the topic on permanent synchronous machines. They are a class of synchronous machines where we do not have a field circuit connected in terms of an exciter. So we've replaced the excitation system by what we call permanent magnets, and these machines. So they will have the permanent magnet basically placed on the rotor of the synchronous machine, right? So because now the magnetic flux that's produced by these permanent magnets cannot be controlled. So what happens is, for those machines, the flux that's passing from the rotor into the air gap and onto the stator side is basically constant. So phi PM is constant. And obviously then the magnitude of E naught is constant for the machine, right? So if you look at the equivalent circuit, it looks the same. For example, this is so for this motor, this permanent magnet synchronous motor, you will have, if it's a salient pole, you'll have your D and Q axis reactances, and that will be your terminal voltage, and this one will be the induced voltage due to the permanent magnets on the rotors, right? So as you can see, there are different configurations for the permanent synchronous machine rotors in terms of placement of the permanent magnets in the rotor circuit. But eventually you'll end up with a phasor diagram that basically looks like this one, where you will have your similar way that we did in the previous section. You will have basically your current. This is a leading power factor motor. So if your power factor is leading, your current I will lead the terminal voltage, and being a motor, obviously the induced voltage is lagging the terminal voltage by a certain angle delta. And the way you resolve this, the current is the same as in the previous chapter, and obviously then IQ is parallel to the induced voltage, and ID is 90 degrees ahead of the current, the quadrature current. And that will be your drop here, IQ XQ, and then you have ID XD there for the basically completing the phasor diagram. So if you look at this next phasor diagram, you can see that the two reactances, which is XD and XQ, basically can be represented in more detailed way, where we're splitting it into two components. And if you remember in the previous chapter, we had that armature reaction due to the D axis and Q axis. So it's the same here. We got the armature reaction that is represented by the reactance XAD and XAQ. So from the phasor diagram, you can see that the component that's basically ID times XAD there is acting opposite to the field, the phasor, which is the induced voltage phasor. So because it's acting in opposite directions, obviously then the effect of that phasor, which is ID XAD, it will demagnetize the magnets. Okay, so this is a form of the circuit which can be used to control the voltage, basically E1, or the terminal voltage, by changing the ratio of ID over IQ, right? So this is a way, because now the permanent magnets, we cannot control the field, we can use the effect of that demagnetization to basically add some control in the field circuits, such that we can adjust the value of the terminal voltage. And this technique is widely used in for speed control, okay, for permanent magnet synchronous motors. So now, if you look at your magnetic circuit theory, if you remember, the relative permeability of the permanent magnets used for excitation is almost 1 for these kind of machines, which means that it would be difficult for basically the flux of the armature reaction to penetrate the rotor along the d-axis, which is the center of the pole for the salient pole machine. So it implies that in such machines, you'll find that XD is less than XQ, as opposed to the synchronous machine with elementary excitation, where you find that XD is greater than XQ, right? So this is particular for permanent synchronous machines. And the torque equation for your motor is basically exactly the same as we worked out. So basically from the equation, you basically have your field component and then your salient component, right? And now, because basically XD is lower than XQ in a permanent synchronous machine, the permanent magnet machine then basically the torque that's due to the saliency, right? So basically this component here is basically less than 0, meaning that it's negative, right? For the this component is negative in the equation, and hence what it's doing is, if you look at this figure here, initially, if you remember, if you have the salient component basically in the negative axis, it means that basically we flipped this salient pole effect of the machine basically by 90 degrees. In other words, so now because you can see it starting in the negative region and then going into the positive region. So when you add this curve to the field excitation curve, the resulting curve now is basically opposite to what we saw in the previous chapter. Okay, it's shifting basically the maximum torque, okay, which at a value that's more than 90 degrees, whereas for an elementary excitation of the synchronous machine, normally your permanent, your maximum torque or maximum power is below 90 degrees, right? So here it's basically opposite to the salient pole machine with elementary excitation, where delta max is less than 90 degrees, whereas here it will be greater than 90 degrees. All right. So just to have we will demonstrate a few questions in just to illustrate this concept. If we look at right, so basically in question 1 of the permanent magnet synchronous machine tutorial, you'll find that it's the question 1 is asking you to compare the permanent magnet synchronous machine torque angle to that of a salient pole machine with elementary excitation. So obviously then you have to focus on this part, that the shift due to the saliency is that it's basically you draw this curve and you show that now it's shifting the maximum torque basically at an angle which is higher than 90 degrees. And you can draw the other one for the elementary excitation and show that the maximum is below 90. And then you can discuss the reason for that is because the ratio, okay, so xd is less than xq for a permanent magnet synchronous machine, whereas for the one with elementary excitation, your xd is greater than xq. Right? So that's question one. Question two, basically, it's looking at a permanent magnet synchronous motor where the d-axis and q-axis are equal. Okay, so the moment they become equal, it means that now the saliency effect is cancelled, right? So if you look at the equation for torque, you have xd minus xq. So if you have equal xd is equal to xq, basically this term becomes 0, and then obviously the whole component of the salient part becomes 0. So what happens is the machine now will basically behave as a cylindrical rotor instead of a salient pole machine, right? So if it's behaving like a cylindrical motor, obviously your power equation will change, okay, because now the salient part basically is cancelled out, and then your analysis becomes more like the analysis in the electrical machines 2 course, where the equation for power is simplified. Okay, so I'm just going to try and pull out the solution for this question 2. So the power developed is basically given by this equation here, right? So you have basically your field excitation part and the salient effect of the machine. And since we've said that ID is equal to IQ, basically this whole component here becomes 0, and then you can just substitute the values to get your power developed. So from this, basically they've given you the rated voltage and the value of XD, and so remember that this is line to line and this is a star connected machine. So if you look at the solution, as you can see, I've converted the line value to the phase value, okay, and also they've given you more information in this question. So basically they've given you some information that the motor basically when it operates at 45 degrees power angle, the internal induced voltage is 127 degrees per phase. So basically they've given you E naught, and as you know, for these machines, the value of E naught now is basically determined by the permanent magnet, right? So if you look at this here, so I've replaced E node by 127, and this is V1, which is your terminal voltage per phase divided by √3, and XD I've replaced it by 1.1, and they've given us the angle, which is 45 degrees, so you can work out the three-phase power developed for the motor. Okay, so I've derived just if some further phase diagram and equations for the motor. If you're representing the stator resistance. So for salient pole permanent magnet machines, basically, if we want to represent using this phasor diagram here, if you want to write the equation for V1, basically the terminal voltage, so this equation here, E naught is equal to, so I've resolved the voltage V1 across angle delta to get this V1 cos theta, and I've added this part, which is IDXD, so that's the full part here, and then you need to extract this small section here, which is IQRS to get the E naught, right? So that's for a leading power factor permanent magnet motor, and also V1 sine delta, so that's resolving this vertically here along ID, so that will give you the component here. Okay, so this component, which is V1 sine delta, is basically the sum of these two phases. So that's IQXQ plus IDRS. Okay, so this is the two equations that represent um, the motor operating in leading power factor. So when you move to lagging power factor, as you can see, now I've placed the current in lagging power factor mode, and I've basically drawn the phasor diagram again for a lagging power factor. So now you'll have your angle delta, and that's the angle phi. Again, you can see now, basically to get E naught, you have basically 1, 2, 3, 4 phasors to consider, and these are the two equations that you're going to use. For E naught, it's basically V1 cos phi. Okay, so we are resolving again to get this phasor along E naught. So that's V1 cos phi. And as you can see now, you have basically those two phasors to consider, right? So that's, you need to extract IDXT, which is this section here, and IQRS, which is this section here, and then you can end up with E naught. Okay, so that's equation 1, and equation 2 is resolving V1 basically at a quadrature angle, so opposite to delta, and that will become V1 sine delta, and that's looking at this component here and this one here. So as you can see now, you have this one acting opposite to IQXQ. So now your component of V1 sine delta will be this phasor, and then basically if you project it here, you see you need to extract this part here. Okay, so it's IDXQ minus IDRS to get this component, which is V1 sine delta. So from equation 1, you can basically make IQ the subject of formula, and then you can replace it in equation 2, and you end up with equation 3, basically, which basically allows you to work out what is the axis current in the motor. And also I've rearranged equation 2 in equation 1, and I've basically worked out how to get IQ, which is the Q axis current. Okay, so the total input power due to the current components in phase with the terminal voltage, right? So the current that is in phase with the terminal voltage will be basically this equation here, which is equation 5. So that's the two components there. So I've resolved ID cos delta, and that's so basically I have this equation here for ID and IQ here, right? So this is equation 3 for ID, and this is equation 4 for IQ. And when you write the full equation for the input power for the motor. So basically, we take the component that's basically parallel to the terminal voltage. So that will be basically IQ cos theta, right? So this is IQ. So if you resolve it, it will become IQ cos theta. And this is ID. And for you, the component that's along the terminal voltage will become ID sine theta, okay? Because this angle is delta here. Right? So this is how the equation is written for the input voltage. And from equation 1 and 2 that we derived earlier, which we have V1 cos phi, V1 sine delta, those two equations we can basically substitute in equation 5, and you end up with this equation 6 here, okay? And this equation 6, I've rearranged it. So you have 3EIQ, and the component here is basically neglecting the stator resistance, okay? So if we look at question 2b, they asked us basically to calculate the power developed by the motor if it operates at 45-degree power angle, right? Given that the induced voltage for part B is 100 volt, right, and the armature resistance is 0.2, okay? So if we look at this equation here, equation 4, I've basically worked out, given the data provided here, what is IQ, right? So from the equation that I worked out for IQ, let's go back, let's have a look. So this is the equation that we've derived. So I've substituted the value in that equation there for IQ and worked out the value of IQ, right? So if you have the power for IQ, then you can basically determine the power developed using equation 7, right? So equation 7, basically I've substituted the value of E naught and IQ there, okay? And since ID is equal to XQ, so obviously this component becomes 0, and then you can basically work out the power developed. Right, so let's have a look at the next question, which is a permanent magnet synchronous motor where again the d-axis and q-axis are equal, and we have the value of xd equal to xq to be 0.9 ohms, and we also been given the data that when the motor runs as a generator, the no load terminal voltage line to line is 60 volt, okay? So which is telling you that when the motor is running at no load, okay, so you have only the field due to the permanent magnet that's acting on the machine, and obviously it's generating a voltage which is 60 volt, right? So remember that we're at no load condition, your terminal voltage will be equal to the induced voltage, right? Because the current that's passing in the stator side is 0. Okay, so in other words, now they are basically giving you the value of E naught, right, which is E naught line to line. If you turn the operation into motor mode, you know what will be the induced voltage for the machine. So now they said calculate the power angle if the machine develops 3 kilowatt power working as a motor and is supplied by 65 volt. So now we are applying 65 volt, which means now the terminal voltage is 65 volt, and we want to basically work out what is the power developed. Right, so let's go back to the equation that we've presented earlier. This is your normal power equation for a um, salient pole machine. And again, as they've given us xd is equal to xq, so that's 0.9, which means that obviously this component will basically become 0, right? And you will only have the field component in your machine. So so now also they've given us the information about the terminal voltage at no load, and so we know that eventually E naught is equal to 60 over root 3 volts, so that's the value per phase. And the terminal voltage now 65 volt is applied at the terminal line to line, so then the terminal voltage per phase is 65 over root 3, and they've given us the power developed, right? So substituting those values here, we can basically solve for the angle delta, okay? Because we know what is V1, we know what is E naught, and we know what is XD, right? So we can solve for delta. So delta comes out to be 43.81, okay? So the maximum power for the machine will be, since it's behaving as a cylindrical machine, the maximum power occurs at sine delta being equal to 1. In other words, that your delta is 90 degrees. So we can use that to basically determine the maximum power. Okay, so the sine delta is 1, and you substitute the value for terminal voltage and induced voltage, and you can get the three-phase maximum power output of this machine. Okay, so since this week we're not going to meet on Friday, what I would advise you is to basically go through the next tutorial, which is on the permanent magnet machine, and basically practice the questions that has been given in the TUT, and make sure that you understand the derivations as well as the calculations that I've presented for the permanent magnet machines. So at this time, I would like you guys to allow some interaction. If you have any questions, please unmute and you can ask your question.